The sector fuel and timetables comprise fuel and time for takeoff, climb to cruising altitude, cruise, and descent to 1,500 feet. For each cruise procedure, maximum, intermediate, and long range, there are several tables arranged according to temperature and arrival weight. The appropriate table for the arrival weight is entered with the required air distance and cruise altitude. Sector time and fuel values can be read off. In our example, we calculated approximately 260 nautical air miles at 31,000 feet, which is the highest possible and thus the least fuel-consuming altitude for this maximum speed journey. It will take 44 minutes and 1,770 kilograms of fuel will be consumed. The takeoff weight is the arrival weight of 34,000 kilograms plus the sector fuel of 1,770 kilograms. So it is a 35,770 kilograms. Remember, we already checked the MTOW for cruise at 31,000 feet. The actual takeoff weight is well below. When the engine and airframe anti-ice bleeds are in use, thrust is reduced at a given N1 and specific fuel consumption is increased. The effect on fuel flow for the sector may be accounted as an increase of 9%. Diversion fuel is obtained from the diversion fuel and time tables, which are based on the long-range procedure and cover the shorter distances and lower altitudes only. Since all sector and diversion fuel tables include fuel for takeoff and initial climb, this will also cover the climb-out after a discontinued approach. For a diversion from 1,000 feet overhead, an average fuel of 120 kilograms can be deducted. For longer diversion distances or higher altitudes, use the main sector fuel and timetables as described before, as well as for diversions whilst at cruising altitude. This may be dealt with by adding the diversion air distance to the sector air distance before entering the sector fuel tables. The diversion fuel and timetables are sorted by weight from 28 to 38 tons arrival weight in steps of 2 tons. Note that this time the arrival weight at the alternate aerodrome is meant contrary to the sector fuel and timetables. Let us carry our example and calculate a diversion of 120 miles sector length and optimum altitude. The wind is calm. The arrival weight at alternate will be around 33 tons as the diversion takes approximately 900 kilograms of fuel. The optimum altitude for diversion is 21,000 feet as we are slightly faster as at lower levels with the same fuel burn. After interpolation, we end up at 25 minutes and approximately 890 kilograms of fuel for an arrival weight of 33.1 tons. Regulations require an Avro-RJ operator to carry holding fuel for 30 minutes at 1,500 feet above the alternate airport. This is also called final reserve fuel, and an emergency has to be declared by the pilot in case he or she has to use this fuel in flight. Total fuel flow for holding with all engines at optimum speed is given in two holding fuel flow tables for flaps up and flaps 18 at ISA. Allowance is made for the effective drag increase involved in 5-minute circuits using 25 degrees of bank. Total fuel flow is increased by 60 kilograms an hour for every 10 degrees Celsius above ISA and reduced by 60 kilograms an hour for every 10 degrees Celsius below ISA. Tables for holding at flaps up and flap 18 with all engines operating are contained in the FDH, as well as those tables here which deal with fuel flow at optimum holding speed with 3 or 2 engines operating. The engine out holding tables are valid for flaps up only. Temperature corrections are the same as for all engines operating. Before takeoff, 21 kilograms and 3 minutes should be allowed for starting engines and flight deck checks. Taxiing consumption is 14 kilograms a minute on all 4 engines or 9 kilograms a minute with 2 engines stopped. Circuits. Fuel consumption in the circuit with flaps 18 degrees and landing gear extended is approximately 2,200 kilograms an hour. Approach and landing. Allow 67 kilograms and 3.5 minutes for a straight-in VFR approach from 1,500 feet, or 143 kilograms and 5 minutes for an IFR approach starting at the final approach point, waypoint, or fix. An aircraft weight and balance manual is provided for each aircraft. The manual contains all specific loading limitations and information. The center of gravity must always lie between the forward and aft limits defined in the envelope of the center of gravity diagram in the aircraft flight manual. The data in the diagram depends on the series and the modification standard of the aircraft. The in-flight and zero fuel limits are shown with flaps and landing gear retracted. The takeoff and landing limits are shown with landing gear extended. The center of gravity datum is at Fuselage Station AXO 1,138.25 centimeters for RJ-70 series aircraft, at Station AXO 1,249.2 centimeters for RJ-85, and at Station AXO 1,383.8 centimeters for RJ-100. The aircraft must be loaded in accordance with the aircraft weight and balance manual and within the limits placarded in the baggage and stowage compartments. There are 4 maximum weight limits: the maximum total weight authorized or maximum ramp weight, MRW, the maximum permissible takeoff weight, MTOW, the maximum landing weight, MLW, the maximum zero fuel weight, MZFW. The center of gravity diagram is also given on the associated manual load sheet. Computerized load sheets show the data in digital form. The maximum design gross weights and center of gravity limits are shown graphically in this envelope chart. These are the absolute limits which must not be exceeded by the airplane's center of gravity in any takeoff, flight, or landing configuration. Ensure that the airplane's center of gravity remains within the center of gravity limits by accounting for airplane balance with all load conditions during takeoff, flight, and landing. When developing an approved loading schedule, appropriate constraints must be established and applied to the center of gravity limits to account for changes in the airplane balance conditions as due to fuel usage or density variations, gear movements, and passenger seating and cargo location variation. This chart is an example for an RJ-85. The center of gravity and weight limits vary for the RJ-70 or 100 and may further vary for individual aircraft. Observe the different forward and aft in-flight and takeoff landing CG limits at zero fuel, takeoff, and landing weights. We will now discuss the standard mean chord, equal to mean aerodynamic chord, as the example of an RJ-85. All formulas and values are related to this aircraft. The length of the standard mean chord, SMC, is 2.932 meters. The leading edge of the SMC is 1.038 meters forward of the CG datum. In order to express the airplane center of gravity as percentage of the standard mean chord, the following equation is used where arm is the distance that the CG is forward, negative, or aft, positive, of the airplane CG datum. When 0 is put in the equation, we get the CG datum as the percentage of the SMC. The CG datum for this aircraft is 35.4% of the SMC. It can be seen that as equipment, fluids, passenger, baggage, freight, etc. are added, their effect can be considered at moments. The CG is the sum of all moments within the aircraft, expressed as percentage of SMC, as we already know. An index formula is established in order to calculate and add each specific moment to the basic aircraft moment. With a known index and weight, a resulting arm can be calculated by conversion of the index formula. This arm is the distance of the actual aircraft CG from the CG datum. Again, this arm is put in the first discussed equation, and the CG results as percentage of SMC. Most operators use computerized load and trim sheets or even data link load sheets, which are abbreviated forms of the computer load sheets. Certain restrictions